Right, let's just start then by looking at the homework from last week. Quiet, please. Pretend you're at a tennis game for a while, and you have to be quiet because the players are concentrating. Thank you. Right. So the first of the two homework questions was this one, which asks you to use the simplex method to solve this problem. And then it gives you this PHP simplex website, which is probably not the only one, but it's a useful website that you can go on, and it does all the simplex method for you, all the simplex tableaus. So if you ever wonder whether your work is correct or not, you can go and check that what you've done is okay. Obviously, nobody has learned by only looking at stuff. You have to actually do it yourselves before you check the answer, because otherwise it doesn't work. However, if you want to check that it's correct, you can go on that website and it gives you all the answers. The only problem is it uses a slightly different stuff. So we would call this val, and this x1, and this x2, and this s1, S2, S3, and we wouldn't have this, and we wouldn't have this. But otherwise, it's exactly what we do. And the first tableau is, oh, and I think in this case, what it does is for minimization problems, it gives you the wrong sign here. So we would have a -1 and a +1. And then you want to look at the positive entry in the Z, and you find by the ratio test, you find your pivot, and on it goes with these numbers. And then when you see the final tableau has this 0 here, which is what we discussed last week, didn't we? There's a 0 in the objective row of a non-basic variable. P4, well, that's S2 in our terminology, is not in the basis, but it has a 0 in the objective row down there. So if you pivot on here, well, if you try to pivot, then you could potentially, that's what we were doing last week, you could find another optimal solution. Okay, well, this solution already optimal. But you won't here, because if you decided to put S2 into the basis, which would be the leaving variable? Which variable would leave the basis? Any idea? Do you understand my question at all? Yeah? So you can't, if you wanted to pivot because of, well, you don't have to, because 0 doesn't indicate that you have to pivot. What it indicates is that potentially if you pivot, you could find another optimal solution. But your pivot element, so you're looking for the pivot element in this column, and there is not a positive number there. The pivot element always has to be positive. You can't take 0 or a negative number as your pivot element. And so you can't pivot here. So it indicates that something different is going on to what we were doing last week. And it's only slightly different because when you, PHP simplex also does this for you. It plots the feasible region if you only have 2 variables. And in this case, the last tableau corresponds to this basic feasible solution where x1 is 2 and x2 is 6. And in fact, what happens is you would want to pivot in this direction. Well, it doesn't quite give you enough at the top, but better than nothing. And this boundary of that constraint, this line going up, doesn't meet another constraint. Okay, so you wouldn't stop anywhere. You just go and go and go. And it turns out, in this case, that all the points in that half line are optimal solutions. Okay, so in this case, what happens is that we cannot pivot. Okay, so I'll write it. You don't have the table, so just watch. So this is the optimal tableau, or a optimal tableau. But we cannot pivot because there is no positive number. In the S2, well, that's B4 in this case, column. Okay, so we can't find another basic feasible solution that will also be optimal. We found one, which is 2 and 6. However, when we look at the picture, we can see all these points that are also optimal solutions. So this whole half line contains optimal solutions. So as a result, we can say that all the optimal solutions, so logical, yeah, rely on a set. Well, it's x1, x2 pairs of real numbers. Well, x1 has to be at least 2 because everything lies to the right of that point. So x1 is at least 2. Where's my black pen? X1 is at least 2, and it turns out that x2. Okay, what does x2 have to be? The answer lies in the question, really, because when you look at the show, yeah. You want that x1 minus x2 always has the same value. So in one optimal solution, we have x1 is 2 and x2 is 6. So this z, its optimal value is -4, is it? So we want x1 minus x2 to be -4. So what does that give us? This gives us that x2 must be x1 plus 4, isn't it? And so this will be the equation of this line is that x2 is equal to x1 plus 4. And all points that satisfy this have objective value -4. And so they're all optimal. Okay. Any questions about this exercise? Good. So that's exercise 1, and then exercise 2 was a bit, perhaps a bit tricky, but it's a nice trick and quite an easy one. Anybody solved it? No. Okay. So question 2, the answer is when we add these two constraints together. A bit larger. So then 2 added together, what do we get? We get x1 plus x2 plus x3 plus x4 is less than or equal to 5. Well, this happens to be the objective. Okay, so we know that no matter what we do, the objective is never going to be larger than 5. Can we find some values where it is 5? Well, we can. For example, if x1 is 3, x2 is 0, x3 is 2, and x4 is 0, is a solution. What am I writing? Solution with the objective equal to 5. So it has to be optimal, obviously, because, well, because as we've just said, the objective can never be better than 5. And so, so that's 1. So it is optimal. But then also, we can see that in every optimal solution, therefore, x1 plus x2 have to be exactly, the sum has to be exactly 3, and x3 plus x4 has to be exactly 2, because otherwise we wouldn't get to 5 in the objective. That is, I think, quite clear. So in any optimal solution, we'll have x1 plus x2 is exactly 3, and x3 plus x4 is exactly 2. So all the optimal solutions now we have a set of 4 tuples of real numbers, x1, x2, x3, x4. The real numbers, 4 tuples of real numbers, they all have to be non-negative. X4 is greater than or equal to 0, and x1 plus x2 is 3, and x3 plus x4 is, plus x4 is 2. And so every time you find numbers that satisfy this, so you can pick your value of x1 between 0 and 3. x2 follows from the first equation. You pick your number of x3 between 0 and 2. x4 is determined from the second equation, and any such 4 tuple will be an optimal solution. Make sense? Perhaps. Okay, so that's the solution to question 2. Now on the register, you can again mark the number of questions that you solve. Oh dear, I forgot. I'm also sending a handout, so please take 1 copy. Okay, so last week's topic was LP degeneracy. Where's my pen again? Anybody found my pen? Oh, I have found my pen. This week's topic is LP degeneracy. Just like it was but there is a second kind of degeneracy. And so let's have a look at the following example. Okay, the objective, we don't really care. For example, maximize x1 plus x2, but the constraints are less than 2x1 plus x2 is less than or equal to 9, and x1 plus 2x2 is less than or equal to 9, and x1 plus x2 is less than or equal to 6, and both x1 and x2 are greater than or equal to 0. Now, you try and draw the objective, the feasible region for this LP. Okay, so I'll be doing it, but you can do it yourselves because you know how to do this. Doesn't have to be a very precise drawing. Not done in a very smart way, doesn't matter. This is x2. I have to start again. I did it stupidly. Okay. X1. You got it? Did you get the same picture? No? Yes? Okay. So the feasible region is this think area, whatever that color is. The three constraints, those three constraints, the boundaries are these three lines that I've marked here, and you always have to be to the left and below, or to the left of these lines and below them. And also, there's the non-negativity constraints, which we've covered successfully. So this is a feasible region. Now, can you see some basic feasible solutions? Okay, so for example, this point is a basic feasible solution, if it's not. And it corresponds to when you put all the slack variables into the basis. We've always set that. This is where the simplex method usually starts. And here that you have x1 is now non-zero in this point. So it has to be in the basis. What is 0 is the first slack variable, because the first constraint, 2x1 plus x2 is less than or equal to 9, is satisfied with equality, so that means that the first slack variable would be 0. So that's not in the basis, but S2 and S3 will still be in the basis. Is that clear, what I'm doing? Okay, so the basis is determined. Remember, when you have a basic feasible solution, okay, the important thing is the variables that are not in the basis are 0. The variables that are in the basis are allowed to be non-zero, but maybe they're not always non-zero. But definitely, if something is not 0 in a solution, then it has to be in the basis. And the slack variables, at the same time, they tell you how much the difference is between the left-hand side and the right-hand side in that particular constraint. So when you look at the first constraint, which is the one that's just at the top of the screen, so this one, if you rewrite it with a slack variable, it would look like this. 2x1 plus x2 plus s1 equals 9. So wherever 2x1 plus x2 is equal to 9, s1 has to be 0. And that is exactly all the points on this line. Okay? So on this line, s1 is 0, and so on this line, s1 is not in the basis, roughly speaking. That's the general idea. Now, where the problems start is in this point, because it's a point where x1 and x2 are both 3, but in this point, unlike all the other things that we've seen, you have 3 lines that meet in that point of the 3 constraint boundaries. See that? This one, and that one, they all meet in the same point. Okay. So what happens there is that, in fact, you can have 3 different bases that correspond to the very same solution. Okay? So the bases that can't write and say something else at the same time. It's quite hard. So the bases that correspond to this basic feasible solution are the following. So we know that x1 and x2 definitely have to be in the basis because they're both non-negative in that point. Right? X1 is 3 and x2 is also 3. So x1 and x2 definitely have to be in the basis. But then we need, every basis has 3 variables in this case, because there are 3 constraints. So we need a third variable, and it can be S1, but it could also be S2, but it could also be S3. Okay, so a test question to see if at least anybody, if one person can understand what's going on. What is, in this point, what is the value of x1? 3. What is the value of x2? 3. What is the value of s1? 0. At least one person knows it. So this means that you know S1 is in the basis, its value is 0. So if you had a tableau for this particular basis, that one was there with S1, x1, x2, s1 would look like this. So of course, well, I'm not going to draw the whole, write the whole tableau, but okay, so where it says basis, you would have x1, x2, s1, and the objective. Oops, sorry, now it's starting to appear. When it says x1, then obviously you'd have 1, 0, 0. Where it says x2, then obviously you'd have 0, 1, 0, 0. Where it says s1, you know what that is. Where it says s2 and s3, we don't really know, or we don't really care. Okay, now we just said that the values of x1 and x2 are 3, and the value of s1 is 0, and we didn't say what the objective was, so we have the objective there. And what is degenerate about this is that we have a basic variable whose value in the basic feasible solution is 0. Okay, so this is the second kind of degeneracy. The first kind of degeneracy was when we had a simplex tableau where there was a 0 in the objective row in a basic variable column, in a non-basic variable column. And the second sort of degeneracy is where we have a 0 as the value of a basic variable in the basic feasible solution. Okay. So second kind of LP degeneracy is that a basic variable has value 0 in a basic feasible solution. Okay, so what it means is, in the geometry we've just seen, it means that too many constraints meet in a point. What does too many mean? Yeah, what does too many mean? So how many do we have in this picture here? 3. How many do we usually have in this picture that meet in one point? 2. But where does the 2 come from? Is it always 2? Or is it only 2 because of something? It is indeed the number of decision variables, because when you have 2 decision variables like we have here, then everything is going on in the plane, right? And so the constraint boundaries are straight lines, and where 2 straight lines meet, it's a point. If we had 3 decision variables, so then everything is going on in the 3-dimensional space. Think of this room and its walls being the boundaries, if you like. And where's their corner? There's the corner there. Okay. So we have 3 planes, the planes of the 2 walls and the ceiling, that meet in one point, and they define this this one point. But if you only take 2 planes, you don't get a point. You get a straight line. They intersect. Okay. So you need 3 planes to get a point. And if there was a fourth constraint that goes through that same point, that would be a degeneracy. Okay, so if you have n decision variables and there are at least n plus 1 constraints that all go through a single point, the boundaries, I mean, not the constraints. Constraints don't go through anything, but the boundaries, so the hyperplanes that they define, and that is too many. So too many means at least n plus 1 constrained boundaries for a problem with n decision variables. Okay. Question: is that a problem? Do we have to care that there's a 0 in the value of a basic variable, or is it okay? Who thinks it's a problem? Who thinks it's okay? So we win because I think it's okay. Well, it's mostly okay. Is that a problem? Most of the time, no. Now, look at the handout problem, please, which is this. So obviously this is an artificial problem, which was created by somebody, I can't remember who, some smart person. But it illustrates something that could happen even in a normal real-life problem. It does not happen very often, we'll come to that, but it could happen. So when you're trying to solve this, you start with you have the tableaus on the other side of the sheet. So you start with this tableau, okay? There's nothing, hope it's correct. There shouldn't be anything surprising in this tableau. You just, the usual way, you add 3 slack variables, and this is what you get. Now, there is a big question, in fact, which we've been walking around a little bit and not really solved it quite satisfactorily, is how do we select the pivot element? So what are the rules for selecting the pivot element? Can anybody summarize them for me? It's very roughly. What have we always been doing? Looking at the ratio. First, however, we're looking at which variables should enter the basis, right? So the most negative, which is a nasty expression, but it works. People don't. It's not really. Negative is a yes/no thing. It can't be more. But the most negative, if you like. So the most negative here is the -3/4. It's more negative than the minus. Okay. Now, the second thing is what Jake said. We look at the ratios. So the ratios are, in this case, well, obviously we can't pivot on something that's 0 or negative. So the 0 is not considered. Never pivot on 0, 4. But we have two ratios and they're both zeros. Okay, so the question is, what do we do? I think we've encountered a problem like that before. The ratios were the same. Now we say, well, we can pick any. So in this case, stick to the rule that when you pick the topmost one, I think. So I take this element as the pivot element, S1 will leave the basis, X1 will enter, and when you do the pivot, you get the second tableau, which looks like this. Okay, here, following the same rule, we've got -4 as the most negative, as it were. There's only one positive element in the X2 column, so the pivot element is clearly the 4. There's nothing else you can do. So S2 now leaves the basis, and X2 enters, and we get this tableau, in which there's only one negative entry here. Now we've got ratios 0, 0, and 1, so we could pick either X1 or X2 to leave the basis, but as I said, I'll go for the topmost one. There's a draw, there's a tie. So I take X1 to leave the basis, and maybe I'm wrong, but nothing tells me I'm wrong, really. I get the next tableau, it looks like this. Okay, again, I pick the most negative one. The ratio is 0, 1, and it's 2 over 21 here. So 0 is less than something, so I have to take 1/5. Can't take negative. What next? Well, next I get this, and then I get this, and then I get this, if I follow my rule. Okay, that was a bit quick, but you can check that it actually follows my rule. Not very good, is it? Have you realized what's happened? Back to the beginning. So the simplest method is done, right? It can't find the solution. This is not the optimal solution. It's I forgot to bring the actual optimal solution. Are we running out of time? It's good. So it will look like I just ran out of time, not that I forgot to bring the optimal solution. Okay, this is not the optimal solution because if you take, what was the problem again? Yeah, if you, for example, if you put x3 to be 1, okay, and everything else to be 0, I think if x3 is 1 and everything else is 0, then you get a solution where the objective is 1/2. Whereas in all these solutions, the objective was always 0. Okay, so it's never improved. The simplex method has never found an improvement. Okay. So what is the conclusion? or not? See, some of you agree. But no, in fact, it's not true. The thing is, there are two things, two reasons why this claim is not true. Firstly, in practical problems, it almost never happens. And when it does, there is a way around it that you can shake it up a little bit to get rid of the degeneracy. Okay, so you take some random changes in the constraint, you change the constraints a little bit, and that's like shaking the constraints around a little bit. And then instead of all those constraints that were meeting in one point, they move a little bit around, and you'll get a couple of points around rather than just the one. So if it does, the simplex solver. So this thing is technically called perturbing the problem a little bit. And perturb the constraints slightly. And the degeneracy disappears. Okay, then when you get out of the cycling, which would cause the simplex method never to find the optimal solution, you can get back to the original values in the constraints, and everything works nicely. So that's the practical solution of this risk. And in theory, so I told you there was a name for the rule of selecting the most negative element. You remember that? It was called Danzig's rule. So Danzig's rule to select the entering variable. So that's the most negative rule. Is not the only one possible. There's also something that's called Bland's rule. Okay. Bland's rule, what it says is that you should take the leftmost negative entry in the Z row. So it's called the least index, but if you order all the variables that are appearing in your problem, or you actually order them like this, right? So x1, x2, x3, and then all the slack variables s1, s2, s3, and then you just look for something that's negative in the Z. But you don't look for the most negative. What you do is you look for the first negative you find reading from left to right. Okay, so take the leftmost negative entry in the Z row, and with Bland's rule, one can prove that this kind of thing never happens. So with this rule, provably there are no cycles. Cycling means you go through a couple of bases in a cycle, like in a loop, and you never get out of what you're doing. Where's everybody going? Do I want to say anything else? Any questions? Yes. You can't really. Okay. I'm out. I'm voted out. So see you later.